Hi everyone, I'm Sierra, and if you clicked on this, it's because you're interested in hearing me explain more about the research that I've been working on. As of filming this, I just finished my third year of grad school at Michigan State University, and this talk is really a culmination of all the work that I've been doing throughout my graduate career, which all surrounds hydrogen-triggered X-ray bursts on accreting neutron stars. So let's jump into some background. Neutron stars will form when massive stars collapse. They're incredibly dense objects. Think of something about 1.5 times the mass of the sun, all squished down to a radius of about 12 kilometers, which in most cases is about the size of a major city. In this case, if you take Lansing and East Lansing as a major city, I just had it centered on Michigan State. Specifically, the types of neutron stars that I study are in low mass X-ray binaries, which means it's a neutron star and a low mass companion. Now, over time, these will orbit each other, and the companion star will lose some of its mass via Roche lobe overflow. This will then form into an accretion disk around the neutron star. Zooming in a little closer, we can see that neutron star at the center of the accretion disk. And to fully get a sense for what I'll be talking about, I'm going to cut out a cross section of the neutron star. I'll move myself over so you can see it. So at the top here is going to be the surface of the neutron star, and at the bottom is where the core starts. Now, on this diagram here, it looks like the envelope is quite big, but that's because we have it inflated, because a lot of interesting physics happens here. But if you look down here, this is only showing about a kilometer into the neutron star, and if we remember back from the intro of the neutron star being a radius of about 12 kilometers, 1 meter does not really make up a lot of the neutron star. However, as I said, a lot of interesting physics happens here and happens to be the subject of my talk. So we're going to talk about it. So as the material and the accretion disk go through periods of instabilities, some of that material will fall on the surface of the neutron star and will increase the temperature and the pressure on the surface of the star and start to burn hydrogen and helium only a few meters into the star. This can cause thermonuclear runaways, which we then observe as X-ray bursts. These X-ray bursts last on the order of tens to hundreds of seconds and recur on the order of hours to days. The types of X-ray bursts that occur will depend on the accretion rate, the pressure at the surface temperature, and the fuel ignited or burned. So here's an example of three different light curves. On the side here, we have luminosity, and on the x-axis, we have time. These are example of three different types of burst. The first one at the top being pure helium burst ignited on an ultra-compact system. In this case, there is no hydrogen at all in the fuel. In the middle case, it's a helium-rich burst ignited after all the accreted helium has been exhausted. This happens at lower accretion rates because that gives it more time for all of the hydrogen to be exhausted into helium. And lastly, at the bottom, we have a mixed hydrogen-helium burst, which happens at higher accretion rates. This is where all of the hydrogen does not have time to sufficiently burn to helium before the helium ignites, so it burns both of them in the burst. However, these are all helium-triggered bursts, and if you remember from the title of my talk, we're missing a whole regime here, the hydrogen-triggered bursts. Here we see two light curves, which were the subject of my first paper. On the left, we have NICER from 2019, and on the right, we have one from RxCE in 2005. Now, on the x-axis, we have time in days, which really show the period of active accretion when the material is falling on the surface of the neutron star. And on the y-axis, we have the count rate. Now, in both cases, we see something really weird here that we haven't really seen before. A so-called weaker burst, which even by eye you can see is about an order of magnitude fainter than the typical bright burst that we usually observe. Though on the RxCE one of them unfortunately got cut off, but we think it should have peaked much higher. In both of these cases, in my paper, we argue that these are likely candidates for hydrogen triggered bursts instead of our typically seen helium triggered bursts. Zooming in closer to the weak burst from the nicer observation, we can see this light curve has its own unique profile shape compared to these other helium triggered bursts on the right. We argue in my paper that this burst was instead triggered by unstable burning of hydrogen via the CNO cycle, and then at some point the temperature threshold reaches the point where it switches to hot CNO instead, which causes this tail after the burst, which is an offset from where it was initially before the burst. So if you go into NASA's ADS and you type in X-ray bursts, you'll see a chart that looks something like this. This shows you the number of papers published that have to do with X-ray bursts. And just for fun, I can put in the two X-ray detectors that I've been talking about, RXTE and NICER. Yes, there are more, but these are just the ones I've highlighted in the talk. And it's cool to see a little bump in papers here after these detectors start observing. But after decades of researching X-ray bursts, we can say, wow, that's really cool. We have two never observed before bursts. Like, let's even say worst case scenario that these aren't hydrogen triggered bursts. They're still really, really weak and really odd. And so that's really cool to see something that is such a different behavior and to explore the physics of it and understand more about our universe. But being scientists, we then come with the daunting question that follows this and say, but only two? Why are they so hard to find? Well, one of the reasons, and again, we only have two of these, so take it with a bit of a grain of salt here. I'll highlight where these weak bursts occur in the period of active accretion. Both of these are occurring early onset of the accretion, only within a few days, about 1 to 3 days after the onset. So it would be quite easy if we don't know when the systems are going to burst, and often we don't know when the systems are going to burst, to unfortunately miss the beginning part of that period of active accretion and only see the following bursts on either side. Recently, there's been a team involved in optically monitoring different transient systems to see if we can get an idea of when these different outbursts might occur, preceding the beginning of it. Using the Los Compras Observatory and the Falks Observatory in Australia, this team has been doing an optical monitoring campaign. In fact, this campaign is part of the reason that NICER was able to start observing in the light curve that I showed you so early on in the period of active accretion. Because here in this box, we see the optical start to rise, which precedes the rise of the X-ray, and then here where NICER started observing. And this allowed the NICER team to start observing really early on in the onset of accretion. Okay, so now we've discussed one idea for a condition that might be needed for hydrogen triggered bursts to occur, and that was being confined to the early onset of active accretion. This could be causing a sample bias. Maybe these weak bursts do occur a lot. We just haven't been able to observe that early onset of active accretion, so we've been missing them a lot. Or it's possible that also maybe they're just rare, but we have to take more observations to really find out. So to dive into a further condition, let's dissect this diagram, which I know has a lot going on, so I'm going to take it step by step. On the x-axis, we have column density, which if you've never heard of it, is kind of a proxy for pressure, or you can think of it as the amount of material as you look down radially into the neutron star. And on the y-axis is temperature. These solid lines here are called ignition curves, but as you go up the ladder, it's going to be increasing in accretion rate. And the idea here is that as you follow along one of these curves, these solid curves of an accretion rate, then you will then reach this condition here with the dotted dash lines or the dash lines where hydrogen will ignite, or up here where helium will ignite. So as we're focusing on the hydrogen ignition here, we see that relative to helium ignition, we require lower accretion rates for the temperature and the pressure to be such that hydrogen will ignite. We can also use this graph or this figure to look at the temperature on the side. We see relative to helium ignition, we need a cooler surface temperature. So this requires a cool neutron star. Now moving forward into the work I've been doing this last year into computational astronomy. We have two observations, but we need to understand it better. And one way to do that is to start doing some simulation work with MESA, which is a stellar evolution code. Now, in order to simulate our neutron star, I brought back up our cool neutron star buddy, and we actually can um, simplify the physics here and delete the core entirely. We don't need to simulate it because all the interesting physics that we're interested in is happening in the surface, only a few meters into the star. So instead of the core, we get around it by just putting a helium or an iron layer and then accreting on top of that iron layer. So if we choose typical parameters for a neutron star, a low accretion rate, and a accreted material with solar composition, we get something out that looks like this as a light curve. However, I'll remind you what we had from the observed burst, and it's not a similar profile shape at all. Though you may notice the y-axes here are different, so I can put up the inferred peak luminosity of 10 to the 37 ergs per second, and as you can see, the mesa burst is definitely not getting bright enough. So that must mean that there's something missing. There's some sort of physics going on that either we are missing or don't understand. How is it possible? Because we observed a burst, but we're not seeing it come out right in our simulations. One thing that my team and I discussed was going back to a classical novae argument, where they were seeing hydrogen burning at energies and rates that only made sense if somehow the metallicity, and specifically the CNO, was enhanced. And this could be an interesting twist to try here. What would happen if we increase the metallicity in our accreted material, for example? So if we increase the metallicity to 20% in the accreted material, look at this profile shape, which looks very similar to the observed burst, even though it may not be as bright. So what if we do this over a range of metallicities and see what happens? So here are all the light curves that I got out using a range from 0.01, which is solar composition, all the way up to 30% metallicity in the accreted material. And already we can see some really interesting trends happen. We see the luminosity of the tail changes with metallicity, and the duration of the tail changes with metallicity. And the inset here shows us the peak of the burst and how that changes with metallicity. We also see the observed burst overlaid on the light curves, and though we never get quite bright enough, we're doing much better than we were before with just our typical parameters in solar composition. Now, if you have alarm bells going off in your head, that is fully justified. 30% metallicity is quite high for an accreted material composition and likely is unphysical. However, this happened to us too, and we wanted to investigate a little further. So looking at this figure here, if you're again not familiar with column depth, if you have 0, that's the surface. And as you increase in number, that's deeper into the neutron star radially. So we looked at where the material ignited, how deep it was in the star. And the hatched blue part is where the observed burst's estimated column range was. And as you can see, as you increase in metallicity, you get shallower and shallower uh, in the neutron star where the fuel ignites, which is not at all what we estimated for our observed burst. We estimated it to be a bit deeper, which is what it's showing us for lower metallicity around 0.06. And so this is showing us that, yeah, this probably isn't the way it really happened. There's some other thing that we need to explore that's causing this increase in metallicity. One other idea we have for the future is to look at diffusion, which would cause the heavier ions to sink relative to the lighter ones, which would then also enhance the CNO at the base of the layer. Okay, so if you've made it this far, you've listened to me talk a lot about all my research. So I'd like to recap all the main takeaways. So the conditions for the hydrogen triggered bursts that we talked about is that they're confined to the early onset of accretion. They happen at lower accretion rates and require a relatively cool neutron star. Now, hopefully, this purple one will be addressed with the optical monitoring of these systems, and ideally, it will also increase observations of hydrogen triggered bursts to add to our sample size. On the simulation side, we see that there must be enhanced metallicity somehow to get to the peak luminosities that we're seeing. However, that may not be because of the enhanced metallicity in the companion star, but instead, maybe there's some other process that we're missing that we need to explore, such as sedimentation, which would also enhance the metallicity at the base of the layer. Thank you so much for listening, and if you have any questions, feel free to reach out to me by email or any other way that you find.